You know, we've all been on a plane, but have you ever stopped to think about what's keeping it perfectly balanced thousands of feet in the air? Well, it all comes down to one of the most critical concepts in aviation, the center of gravity, or CG for short. And understanding it is absolutely key to an aircraft's safety, its stability, and even how much fuel it burns.
So, to get our heads around this, let's start with a really simple question. Why is an airplane basically a giant flying seesaw? Yeah, I know it sounds a little weird, but trust me, this one analogy is the key to understanding everything we're about to talk about.
And that seesaw idea takes us right into our first section, the airplane's balancing point. This is where we're going to get to grips with what the center of gravity actually is.
Okay, so the center of gravity, it's this single, invisible spot where you can imagine the entire weight of the aircraft is perfectly concentrated. Think about trying to balance a model airplane on the tip of your finger. You know that one little point where it balances perfectly without tipping over? That's its center of gravity. It is the pivot point for the entire machine.
But here's the catch, and this is absolutely crucial. That point isn't fixed in one place. It's totally dynamic. Every single time a passenger moves or cargo gets loaded, or even as fuel is burned off during a flight, the CG shifts. And that's exactly why pilots have to do a weight and balance calculation before every single flight, just to make sure that CG stays within a very specific, very safe range.
So now that we've got our balancing point, we need to understand the forces that are acting on it. And this brings us to the three key forces that are constantly in this delicate aerial dance.
First up, we've got weight. This one's pretty simple. It's just the force of gravity pulling the aircraft down, and it acts straight through that center of gravity point we just talked about. Easy enough. Next, we have lift. This is the amazing upward force the wings generate that keeps the whole thing in the air. Now, what's really fascinating here is that lift acts through its own point, called the center of lift. And the key thing to remember is that this is a totally different spot from the center of gravity. And this is where you start to see the real genius of aircraft design. In any stable airplane, the designers intentionally place the center of gravity, that pivot point, ahead of the center of lift, which is where the wings are pushing up.
Okay, so think back to our seesaw for a second. If the pivot point is forward of where you're pushing up, what's going to happen? The nose should constantly want to dip down towards the ground, right? So why don't airplanes just nosedive all the time?
Well, the answer is our third key force, something called tail downforce. That horizontal stabilizer on the tail, you can think of it as a little upside-down wing. It's actually generating a downward force. It pushes the tail down, which pivots the nose up and perfectly counteracts that nose-heavy tendency. It's the secret ingredient that keeps the whole system in balance. And once you understand that third force, it totally changes how you think about the work an airplane's wings are actually doing. So let's look at what we could call the real lift equation. You know, in basic physics class, they teach you that for something to fly straight and level, the upward force has to equal the downward force. So for a plane, that would just be lift equals weight, right? Well, it turns out that's not quite the whole story. Here's the reality. The wings have to generate enough lift to overcome two separate downward forces, the total weight of the aircraft plus that tail down force we just talked about. So the wings are actually working way harder than we thought, fighting against both gravity and the force created by its own tail. So here's the takeaway. Where the pilot decides to load the weight directly impacts how hard the tail, and in turn, the wings have to work. Let's see how this plays out when we compare a forward CG versus an aft or rearward CG. This table really sums it up perfectly. A forward CG makes the plane more stable, but it's less efficient. An aft CG, on the other hand, is less stable but more efficient. It also changes the plane's stall speed, and most importantly, how easy it is to recover from a stall. Let's break down why that is. Okay, so if your center of gravity is way up front, the plane is really nose-heavy. To keep it balanced, the tail has to work overtime, creating a huge amount of downward force. Well, that means the main wings have to create even more upward lift to compensate for both the weight and that big tail downforce. And to do that, you need a higher angle of attack, which creates more drag. More drag means you burn more fuel. It's a whole chain reaction. Now, on the flip side, if you shift that CG toward the back of the plane, it's a lot less nose-heavy. The tail doesn't have to push down nearly as hard. And that means the wings don't need to generate as much extra lift. This lets the plane fly at a lower angle of attack, which means less drag, and that translates directly to higher cruise speeds and much better fuel efficiency.
And this all sets up the fundamental trade-off that every single pilot has to manage on every single flight, this constant balancing act between stability and performance.
A forward CG is the stable, safe choice. Think of it as being, well, nose-heavy and anchored. The plane naturally resists big changes in motion. And here's the best part. If the aircraft stalls and the wings lose lift, that heavy nose becomes a built-in safety feature. It helps the plane automatically pitch down, which lets the pilot regain speed and recover much more easily.
An aft CG is the performance choice. The aircraft is more nimble, more responsive, and way more efficient. That's great for your flight time and your fuel budget. But it definitely comes at a cost. The plane is less stable, and if it stalls, you lose that natural nose-down tendency that helps you recover. It can become incredibly difficult to get back under control.
And this isn't just some theoretical problem. This quote right here sums up the danger perfectly. Flying with the CG too far back is incredibly risky because it can cripple a pilot's ability to recover from a bad situation. You have to know and respect the aircraft's limits, period.
And that's really the big thing you should take away from all this. Managing the center of gravity isn't just a homework problem for student pilots. It is a fundamental, non-negotiable part of the pre-flight routine. It directly determines whether a flight is going to be stable, efficient, and above all else, safe.
So let's wrap this up with a question to put it all together. Now that you know about this constant trade-off between stability and efficiency, if you were the pilot on a long cross-country flight, where would you want your center of gravity to be? Would you load it as far forward as possible for maximum safety, or would you try to get it further back for better performance and fuel burn? It's the kind of decision pilots have to think about every single time they fly.